So when we look at XY scatter plots or correlation coefficients to try and unravel our linear associations, that implicitly assumes that for each fixed change in x or each unit change in x, I'm going to get some fixed change in y, right? So regardless if I'm increasing x from 20 to 21, I'm going to get the same impact in y if I increase x from 120 to 121. That doesn't always work in practice, right? Think about advertising. I spent $100 on advertising, I get a lift in sales. I spent another $100 on advertising, sales increase, but not to the same degree as they increased last time. And I spend a third $100 in advertising, again an increase, but not as much as the second $100 and definitely not as much as the first $100. So yes, there's a relationship between advertising and demand. It's just not linear. It's some sort of non-linear relationship. We're getting these decreasing incremental impacts versus fixed impacts over all levels of advertising. So the question is how do I uncover these non-linear relationships? Because if I ignore them, then and try and sort of look at them as linear, I may underestimate them or think they don't exist, right? So we need to uncover these non-linear relationships so we can use those as well in reducing our uncertainty. So think about demand as a function of time in the market, right? So we're going to have some increased word of mouth the longer our product is out in the marketplace, such that the speed of or the increase in sales is increasing in a non-linear fashion. It's actually increasing as a function of time squared, right? So demand is increasing rather quickly the longer we're out there. So if we just sort of look at demand as a function of time and look at a linear relationship, we may underestimate the impact of time upon demand. Whereas if we looked at a scatter plot of demand as a function of time squared, then we get a very strong linear association because we've implicitly built in that non-linear relationship, right? So we've described that relationship well, given we knew ahead of time it was nonlinear and was a function of time squared. But what if we don't know that? What if we don't know it's a function of time squared? How do we uncover that relationship? Well, we can do that using transforms. The most common transform we use is called the natural logarithm. So instead of doing a scatter plot of demand versus time, we do a scatter plot of the natural logarithm of demand versus the natural logarithm of time. And it turns out that relationship is linear and strong. And the actual nature of that relationship links right back to the underlying nonlinear relationship, in this case being a function of time squared. We still would have had a line. The line would have been different steepness, if it was a function of time to the power of 3 or time to the power of 4. So let's think about these things in terms of demand and price, right? So obviously at different points along the price-demand curve, the impact of price is going to differ, right? At lower price points, price is going to drive demand differently than at higher price points. So we have a nascent or underlying non-linear relationship between price and demand. So we can sort of map out that relationship using our transforms. So now we look at the natural logarithm demand versus the natural logarithm of price. And now we have a linear relationship that we can describe. The nice part about that description is that we get these constant relative differences versus our constant absolute differences in our sort of linear world, right? In our linear world, we assume that when x went up 1 unit, regardless of what that was from x from 20 to 21 or 121 to 122, we were going to get the same change in y. That same thing happens in our nonlinear world, but instead of being an absolute increase, it's going to be a relative or percent increase. So a percent increase in X is always going to generate the same percent change in Y, regardless of where we are in our price demand curve.